to the session 7 of module 4. In this session, we are studying about designing of sequential circuits from the state diagram. These are the contents that we are studying in this session. First, we'll study about the procedure that we have to follow while designing a clocked sequential circuits. Implementing state diagram using flip-flops. We have to implement the state diagrams that is given using the respective flip-flops that is mentioned in the problem. If they don't mention in the problem, we can consider any flip-flop of our choice. And excitation table of flip-flops. We are having 4 types of flip-flops, and depending on the present state and next state, we have to write the excitation inputs of flip-flops. The design procedure for clocked sequential circuits. We are having 7 steps that we have to follow while designing the clocked sequential circuits from the state diagram given. First step is a state diagram or timing diagram is given, which describes the behavior of the circuit that is to be designed. They will give us the state diagram or timing diagram. That timing diagram or state diagram describes the behavior of the circuit that we have to design. And second step is obtain the state table. State table consists of the present state and next states with the respective input and outputs. Third step is we have to perform the assignment of the states. We have to do the state assignment. And the fourth step is determine the number of flip-flops required and assign letter symbols to the flip-flops. By knowing the number of states, we can find out the number of flip-flops required. Okay, that is 2 power x is equal to y. X is the number of flip-flops and y is the number of states. That is 2 power x equals y, where x is number of flip-flops and y is number of states. If we want to have 4 states in the state diagram, then we require 2 flip-flops to represent that. Okay, and if you are having, let us consider 6 states, then we require 3 flip-flops to represent that. Okay, and decide the type of flip-flop to be used. If in the problem they mention the type of the flip-flop that we have to use, then we have to use that flip-flop only. If they don't mention, we can use any of the flip-flops. Derive the circuit excitation table from the state table. From the state table, we will be having present state, next state. And by having the present state and next state, we know the excitation table for each of the flip-flops. Okay, and depending on the flip-flops that we have to use for designing the circuit, we have to consider that excitation table of the flip-flop, and then we have to write the inputs, excitation inputs of particular flip-flop. In detail, we'll study in the next slide. Step 7 is implement the circuit. After getting the excitation table, that is by considering the present state and next state, we can write the flip-flop inputs by knowing the excitation table of respective flip-flops. And after getting this excitation table, we have to implement the circuit. To get the inputs of the flip-flops, we have to write the K-map. We have to write the K-map for each input. Okay. Let us consider one example. Implement the state diagram shown using JK flip-flop. This is the state diagram that we are considering. Here, the circles, inside the circles, we are having the states. We are having 4 states here. And these arc represents, the directed arc represents the transition from the one state to the other. Okay, and here this represents the input, and here we are not having any output here. We are having only input section. Okay. Step 1. What is step 1? A state diagram or timing diagram is given, which describes the behavior of the circuit that is to be designed. By having the state diagram, we have to design a synchronous sequential circuit. How to design a synchronous sequential circuit? That we'll see now. First step is they will give us the state diagram or timing diagram. This gives us the behavior of the sequential circuit. Next step is design state table. State table, it consists of the present state and next state and the input and output. Since we are not having an output here in this state diagram, we will be having the present state and next states with the inputs. Here we are having the present state. 4 states will be there. Okay, what are the 4 states here? 0, 0, 0, 1, 1, 0, 1, 1. And when x is equal to 0, it will be in the same state. When x is equal to 1, it goes to the state 0, 1. When the present state is 0, 1, when x is equal to 0, it goes to state 1, 0. When x is equal to 1, it will be in the same state. When the present state is 1, 0, it will be, when x is equal to 0, it will be in the same state. When x is equal to 1, it goes to the next state 1, 1. When it is in present state 1, 1, when x is equal to 0, it will be in the same state. And when x is equal to 1, it goes to the state 0, 0. By having these, we can construct a state table. Okay, 0, 0, 0, 1, 1, 0, 1, 1. And the next state, depending on the input values, we are writing the next state. Okay, we are having 4 present state. Depending on x is equal to 0 or x is equal to 1, we are writing the next states. Third step is do state assignment. Here we are having a binary values for the states. We have to assign the symbols for these values. Okay, we are assigning the state A, that is equal to 0, 0. For 0, 1, we are assigning state B. For 1, 0, we are assigning symbol C. For 1, 1, we are assigning symbol D. Here we require 2 flip-flops to represent 4 states, okay, and are designated as Q0, Q1. We are considering the state variables as Q0 and Q1. Okay, that is output of the flip-flops. We are representing as Q0 and Q1. The input variable is labeled as X. In this step 3, we are assigning the states, okay, with the symbols. Here we are having 4 states. Each of the 4 states we are representing it using the symbol, and we are assigning the symbols for the output of the flip-flops. Okay, that is Q0 and Q1. You can take F0 and F1 or F1, F2. It's our wish. We can represent using any symbols, and we are considering the input variable as X. Fourth step is determine the number of flip-flops required and assign letter symbols. We require 2 flip-flops. Okay, we require 2 flip-flops, and we are using 2 flip-flops to represent 4 states, and those are designated as Q0 and Q1, and we are assigning the letter symbols for those, and the input variable is labeled as X. And decide the type of flip-flop to be used depending on the problem. Okay, if they mention the type of the flip-flop that we have to use for designing, we have to use the same one. But if they don't mention, it's our choice. We can use any of the flip-flops. We should know the excitation table of particular flip-flop. And this is the excitation table for the SR flip-flop and JK flip-flop excitation table. This is the characteristic table, and this is the state diagram for flip-flop. Okay, SR, and this is for JK, and this is the excitation table of SR flip-flop. In this problem, we are considering for JK flip-flop. When the present state is 0, and if you want to get the next state as 0, what should be the JK inputs? If you want to get the next state as 0 and the present state is 0, we have to input JK is equal to 0, 0 or K is equal to 1. Here, if you want to get next state as 0, then 0, 0. If you are inputting 0, 0 to JK flip-flop, then whatever present state is there, it remains same. So our inputs to the flip-flop will be 0, 0. And if you want to reset, or if you want to reset the flip-flop, and if you want to get the output as 0, then we can provide the input as 0, 1 to the flip-flop. Okay. Then we will get the next state as 0. When the present state is 0, and if you want to get the next state as 1, what should be the inputs for the JK flip-flop? If you want to set the flip-flop, you have to input 1, 0 to the JK flip-flop. Okay. Otherwise, we have to toggle this, because the present state is 0. If you are inputting 1, 1, then it will toggle the state and you will get 1. Okay. So our inputs to the flip-flop is 1x. X here means J should be 1, but X may change. It may be 0 or 1, but you will get the next state as 1. When the present state is 1 and next state we have to get is 0, what should be the input? Okay, for the JK flip-flop. If you want to get, or if you want to reset the JK flip-flop, okay, our K input should be high. Okay, that is 0, 1. Okay, and here the present state is 1, we have to toggle that. So we can also give the input as 1, 1, which toggles the state, and we will get 0 for this condition. Okay, so what should be the inputs? J may be the 0 or 1, so we are writing x1. Okay, x1 is the input of the JK flip-flop to when the present state is 1 and the next state is 0. And for this input, present state is 1, 1 and next state is 1. J is equal to x. If you want to get the next state as 1 and the present state is 1, what should be the J and K inputs? What should be the J and K inputs? Here we have to make this JK flip-flop to set. For that, what we have to do, we have to input 1, 0 to the flip-flop. Okay, and if you want to keep the present state as same, then we have to input 0, 0. So our input to the flip-flop is x0 when the present state is 1 and the next state is also 1. In this way, we have to write the excitation table, and then we have to get the excitation table for the flip-flops. These are the D and T flip-flops. This is the characteristic table, and this is the state diagram for the flip-flops, and this is the excitation table for that. Here, the excitation table for D flip-flop, if you see here, you can easily come to know that here D input, whatever D input we are considering here D input, it is same as it of the Q next. Okay, whatever next state we have to give, we have to get that input, we can give it for the D flip-flop. Then you will get the same output as the next state, same input as the next state. Then for the T flip-flop, it is the output is XOR operation, so that is T XOR Q. Here We know that T flip-flop, whenever we are providing input 0 for the T flip-flop, whatever present state is there, it remains same. Whatever present state is there, it remains same when T is equal to 0. Whatever present state is there, it remains same. But when T is equal to 1, the present state is toggled. Okay, for 0, 1, we are getting 1, 0. Okay, but for the D flip-flop, whatever may be the present state, okay, the whatever input we are giving for the D flip-flop, that will be our output. That is the next state. Here we are using the JK flip-flop for this problem. Okay, after writing the transition table, that is the present state, next state. Okay, present state and next state. Okay, and the input, we have to get the write the flip-flop inputs by considering the respective flip-flops present state and next state. Here, for example, I will explain you this. Here, present state is 0, 0, and the next state is 0, 0. This we have written by considering the state table that we have got in the last slide. Okay, here 0, when the present state is 0, 0 and next state is 0, 0 and input is 0. 0 when the present state is 0, 0, when the input is 1, the next state will be 0, 1. When the present state is 0, 1 and next state is when the input is 0, next state will be 1, 0. When the present state is 0, 1, when x is equal to 1, it goes to state 0, 1. Then when the present state is 1, 0, when x is equal to 0, it will be in the same state. When the present state is 1, 0, when x is equal to 1, it goes to the state 1, 1. And when the present state is 1, 1, when x is equal to 0, it will be in the same state. When the present state is 1, 1 and input is 1, next state is 0, 0. By having this is present state and next state, we have to write the flip-flop inputs by knowing the excitation table for the JK flip-flop. We know the excitation table for the JK flip-flop. When J is equal to 0, when the present state is 0 and the next state is 0, what is our JK inputs? JK inputs are 0x. When the present state is 0 and the next state we have to get is 1, then we have to set the flip-flop, that is 1x. Okay, here you should remember this because we have to write the K map after that for each of the flip-flops to get the equations, flip-flop input equations to design the circuit. So we have to remember this. If you know the flip-flop truth table, okay, you can easily write this. Okay, when q is equal to 0, when present state is 0, and if you want to get the next state as 1, what should be the JK inputs? If you want to set the flip-flop, we have to input 1, 0. Okay, we have to, the J input should be 1 and K should be 0. Okay, this is one input. And the other one is when, if you want to set the flip-flop, if your present state is 0, we can also give this input 1, 1. Because the JK inputs are 1, 1. It toggles the present state. It toggles the state and you will get 1. So, since the K value is 0, 1, we, instead of 0 and 1 separately, we are writing it as X. Don't care. It may be either 0 or 1. So, and for 0, 0, JK inputs are 0x. For 0, 1, it is 1x. For 1, 0. For 1, 0, if you want to reset the flip-flop, our input should be 0, 1. And here the present state is 1. We can also toggle the flip-flop. So we are writing x here. Okay, it may be either 0 or 1. And 1, 1. When the present state is 1 and if you want to get the next state as 1, then we have to give if you have to set the flip-flop, so I'm writing here X, because here it may be the 0 or 1. If it is 0, 0, whatever present state is there, it remains same. If it is 1, 0, it will set the flip-flop. So this is the excitation table for the JK flip-flop. And here, to write the flip-flop inputs, we have to consider the present state and next state of the flip-flops. Here we are considering the Q0 first, and then afterwards we check for the Q1. Here Q0 of the present state Q0 and the next state Q0, or we can consider Q0 plus here, okay, and Q1 plus. Here when Q0 is 0 and Q0 plus 0, then 0, 0 for 0, 0, then what are the flip-flop inputs? 0x. For 0, 0, 0x. For 0, 1, 1x. For 0, 0, 0x. For 1, 1, x 0. Which means that when the present state is this Q0 and the next state is Q0 plus, if you want to get a particular next state, what should be the JK inputs that we are doing here? Okay. When the present state is 1, next state is 1, what is the input? X0. Present state is 1, next state is 1, X0. Present state 1, next state is 0, X1. Okay. This is for the first one flip-flop, and then other flip-flops we have to check. Q1 and Q1 plus are the present state and next states. And what are the inputs for that flip-flop? J1 and K1. Okay. Here, when Q1 is 0 and Q1 plus is 0, the input for the flip-flop is 0x. Q1 0, Q1 plus is 1, 0 1. For 0 1, 1x. For 1 0, it is x1. For 1 1, you please see this present state Q1 and next state Q1. Okay. When 1 1, it is x0. 0 0, 0x. 0 1, 1x. 1 1, x0. 1 0, x1. In this way, we have to write the flip-flop inputs. Okay. First, we have to write present state and next state columns, and afterwards we have to write the input. Otherwise, we can write the input between the present and next states. And after that, we have to write the flip-flop inputs. Okay. Flip-flop inputs, we have to consider which flip-flop we are considering, and we have to remember the excitation table for that, and then we have to write the flip-flop inputs by considering the present state and next state of the particular flip-flop. And we have to write the flip-flop inputs for the respective flip-flops. In this way, we have to write the table, excitation table from the state table. The simplified Boolean functions for this combinational circuit can now be derived. The input variables are Q0, Q1, and X, and the output are the variables J0, K0, J1, and K1. Now, after writing this flip-flop inputs, okay, here we have to write the K-map in order to get the input equations for the flip-flops J0, K0, and J1, K1. Okay, for that we are considering the inputs for the K-map as Q0, Q1, and X. And the information from the truth table is plotted on the Karnaugh maps as shown. Here, this is the K-map for the J0, K0, J1, and K1. Okay, here we have to consider this flip-flop inputs. For the J0, what is the output? 0, 0, 1, 0, x, 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 x. 0, 0, 1, 0, 0, 0, 1, 0, x, 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 x. Here the inputs, input variables are Q0, Q1, x. And here, after the simplification of this K-map, we will get the simplified term as Q1, x bar. Q1, x bar. Here we are getting Q1 X bar. Here we are grouping these two and we are getting this expression. For the K naught, we are having the terms that is 0, 1, 1 and 1, 1, 1 as high, and here we are having a don't K term. We can group these two, and the simplified term is that is K naught is equal to, here from these two rows we are getting Q1, from this column we are getting X Q1X. Next, for J1 map, here we are having this 1x x1, which makes a quad, and we are getting x. And here we can make two pairs which are adjacent to each other. Here this is one pair and this is one pair. Okay, the main terms are adjacent to each other. So we are grouping these two as pairs. And now what is the term we are getting here from these two, q naught bar into x bar dot x bar, and here q naught x. This is in the form of x NOR operation, that is q naught dot x. Okay, circle with the dot represents the x NOR operation. Okay, in this way we have to derive the flip-flop equations, input functions or input equations. For any flip-flop, we have to follow the same procedure. If you are having output variable, you will be having one extra column here, that's all. Okay, here you will be having, let us consider output is Z, and here for the respective next state or transitions, we will be having the output Z value. If it is a milli-circuit, we will be having the output for each of the transition, and for the Moore machine, we will be having this output for the states. Okay, it depends on only the state variables. It doesn't depend on the X, that is input variable. So we'll be having the output Z. Okay, if it is milli machine, we have to consider Z when X is equal to 0 and X is equal to 1. When it is milli machine, we have to consider Z when X is equal to 0 and Z when X is equal to 1. But for Moore machine, no need of considering the input variable, we are writing only Z. Okay, but for the example that we are considered here is not having any output variable, so we are not writing here output. If you are having the circuit which consists of the output variable, we have to consider another column here where we have to write the output variable Z, and we have to write the outputs here, and then we have to write the K-map for this output also, because we have to design a circuit where we have to mention the output variable also. So we have to remember that. And depending on the flip-flops that we are considering, this flip-flop input section will differ. If it is JK, we are having this. If it is D flip-flop, no need of considering another section here for flip-flop inputs. Whatever next state is there, that will be our D input. Okay, but for T flip-flop, it is for the T flip-flop, we have to consider here the next states for this will change, and for SR also it will change. Okay, D flip-flop only, whatever next state is there, we will get as the D input. But for others, we have to remember the excitation table for each of the flip-flops. Okay, after writing the state table, excitation table, we have to get the write the key maps and get the flip-flop input functions. And after getting flip-flop input functions, we have to write the diagram, logic diagram or sequential circuit. The flip-flop input functions are derived. These are the flip-flop input functions that we have derived. Okay, and now we have to write the diagram. We have to implement the circuit. Here we are having two flip-flops, two JK flip-flops, where we are having two inputs for each of the flip-flop, J and K. Input for this J flip-flop is Q1 dot X bar. Here for J naught, what is the input? For J naught, it is J naught. It is here. We are considering Q1. Here it is Q naught. Here Q1 into X bar, and K naught is Q1 in dot X. By having these equations, we have to write the combinational circuits. We have to write the combinational circuit. This is the input variable X. Here X bar. We have to consider one NOT gate, and what is the output here? X bar. And here we are considering from Q1. Okay, we know how to write the flip-flops. You know how to write the flip-flops. This is J and K flip-flop, JK flip-flop. Here, what are the outputs? Q1 and Q1 bar are the outputs. And here, this is flip-flop 1. And this is flip-flop 0. Here, we have to provide the clock pulses simultaneously because it is synchronous sequential circuit. So, we are writing the clock. We are providing the clock simultaneously to both the flip-flops. And first step while implementing the circuit is first write the flip-flops, and afterwards you check the equations, and depending on the equations you have to write the logic gates, okay, logic circuits, and provide the input to the flip-flops. Okay. Here we are having G naught is equal to Q1 dot X bar, K naught is Q1 dot X, J1 is X, and K1 is Q naught XR X, X nor X. Here J naught is Q1 X, Q1 X bar, K1 is Q1 X, and here J is equal to X and K is equal to here Q naught into Q naught X nor X. So this is X nor operation, X nor gate. Okay, and in this way we have to write or implement the circuit. After getting the equations, okay, you have to first step is write the flip-flops and provide the clock pulse, and consider the flip-flops FF1 and FF2 or FF0 and FF1. Okay, and you name the flip-flops. Okay. After that, we have to provide the inputs to the flip-flops and consider the combination circuit for them for the inputs, and provide the input variable. Okay, and your circuit you will get the circuit. Okay, in this way we have to do the or implement the circuit. For the other flip-flops, if they mention, then we have to consider the same flip-flop. If they don't mention, whichever flip-flop is easy for us. D flip-flop is very easy because whatever next state is there, that will be the D input. So consider the D input if they don't mention any of the flip-flops. It will be easy for us. Okay. Thank you for attending this session.